Hello, everybody. Good morning, good afternoon, good evening to everybody. Thanks for your presentation then. Today, I will be presenting my work on evidence of dynamic transformation under tensile test using a Gleeble machine coupled with in-situ X-ray diffraction. The author of this investigation we can see here are myself, Fulvio, Rod, Gideon, Eden, and John Jonas. We are all from those institutions. And let's go. The outline of my presentation, I will give you a brief introduction. I show the methodology that I used to do this investigation. I did tensile test using a Gleeble machine. Also, I analyzed the stress strain behavior on the flow curves. We applied the X-ray diffraction, and I showed the X-ray diffraction features. The calculated volume fraction of transformed and retransformed ferrite. And also, at the end of this presentation, I will discuss a little bit about the practical implications. As you can see, here we have this image. The main challenge in the field are well known. Applying grade should simultaneously fulfill a quite complex set of requirements. These include excellent weldability, very high toughness and strength over a wide temperature range, and exceptional crack arrestability. The specific sites of the lattice gas and petroleum source require the mechanical, chemical, and technological properties to be stable over a very large range. For example, pipeline, as you can see here in this picture, pipeline should be able to operate at temperature between plus 50 and minus 50 centigrade or even lower. Increasing needs for the transportation of large volumes also require pipelines to operate at higher pressures. This requirement is often solved by using pipes with thicker walls. However, the requirements for pipeline grades are more complex than what was said here, which refers mainly to weldability, strength, and also toughness. The mentioned set of mechanicals like strength, toughness, and crack arrestability, and technological requirements like weldability resulted in the development of the contemporary pipeline steel grades. The only way to control the mechanical properties of this grade is by the control of microstructure and crystallography texture of this kind of steels. And also, this is possible by the designing of an appropriate chemical composition to this material and by appropriate thermomechanical controlling process known as TMCP, that is, by applying the appropriate rolling reduction at the appropriate temperature and employ the right cooling rate. Such an approach is known as, like I said, the mechanically controlled processing, and exactly parameters are dependent on steel chemistry, initial, before rolling, I say, and final plate thickness, and of course, the capacity of the rolling equipment. And also, I will show you that I did this research using the HSLA steel that is known as high strength low alloy steel that's required for the pipeline application. And as I can mention here that the first mentioned like this kind of HSLA steel was mentioned by around 1952 in Europe. And this material was normalized as API grade X52 microalloyed with vanadium. And today, due to excellent properties achieved so far, the X70 steels and X80 grades are still the reference materials of today. And during the rolling process, we have this kind of parameters that can be seen. We have the reversing mill that is plate and roughing. Normally, the interface time between pass between strain is between 8 and 20 seconds, and the strain rate varies from 1 to 30. We are concentrating this one here, the reverse mill, because we are doing research. Our main research are focused on this kind of processes. As we know, this is the static versus dynamic phase diagrams. The static and well-known carbon phase diagram. You can see here that we have the single phase austenite phase field here, where normally the rolling process is applied. But what we have investigated is that by applying a force over the material, this line that is known as A3 temperature line goes up, where this double phase region will become wider. And normally, before the application of the rolling, this kind of dynamic or static diagram can be considered. But actually, what we've been seeing through our research is that ferrite is transformed from austenite due to the application of the rolling. So instead of deforming only austenite, we can see that the volume fraction of ferrite increases. Here we have some previous results, published result from a carbon manganese steel from a temperature of 930 centigrade. That was what a pint meters left. The 7-pass simulation of the rolling process. The indexed phase or austenite, while the black region or martensite, because the quenching process, we know that austenite transforms into martensite. As you can see above the A3 line here, that was expected only austenite. We have a considered volume fraction of ferrite formed. What is like the driving force for this transformation? And what is the total barrier that avoid this kind of transformation? Under stable condition, austenite exists above the A3 temperature. This also depends on chemical composition as well. But we have formulated an approach where we can explain, we try to explain what's happening. First of all, when you see this diagram over here on the right part of the screen, we see that we have this line here. It's to represent the Gibbs energy difference between austenite and ferrite. So 0 here represents the temperature over the A3 line. It means that until 1500, it's mean like above the A3 line. This one is a barrier. Under static situation, ferrite cannot be transformed from austenite because the Gibbs energy difference between those two phases are positive, as you can see. Associated with another barrier to transform ferrite from austenite, it relies on the dilatation, because the ferrite to be transformed will suffer dilatation. It's another barrier. And also we can see the shear accommodation, because this is another barrier, because when the austenite is transformed, we have shear over the austenite phase. It's another barrier. When we add all those three barriers, we have the total barrier that avoid this kind of transformation. So to be transformed, we need more energy than driving force that must overcome the total barrier. Where does kind of energy come from? It comes from deformation. How could you explain this? So first of all, it's a trick approach to explain, but we tried. We did some calculation in main compression test, tensile test, mechanical test inside the ferrite phase field. When you see this chart on the left side, we have here the yield stress of ferrite. We had many results. When you extrapolate this line, we see this trend until here to the point of the delta ferrite passing through the single ferrite phase, increase the temperature, passing through A1 line and A3 line, the double phase region, until the austenite phase region had this extrapolated line. When you calculated the critical stress for the onset of dynamic transformation that I will explain later, how we calculate this one, we saw that inside the austenite phase field, we had this result. So when you make the line, we have this behavior over here. The difference between the critical stress for the onset of dynamic transformation that I mean ferrite being transformed from austenite, this difference when applied by the M, that is this mid factor, the most favored grains. When you apply this one, we calculate, we get this amount of driving force. As you can see, the total energy barrier, we have the Gibbs energy difference between austenite and ferrite, also the shear accommodation, and the work dilatation in terms of the volume. This one was calculated for these formulas, where all the parameters we have here, and we also have this as references. The driving force was all over for the most oriented grains. We took these oriented grains as 0.5 mid factor value. So when we calculate over the range of the temperature above the E3 line, we have this. So the most oriented grains are prone to be transformed into ferrite due to the application of the stress or even the strain over the material. Not all of the grains are transformed into ferrite because it must have the most oriented grains, and we consider the most oriented grains with this mid factor value of 0.5. And here I have some previous results, previous work. When I used a Gleeble machine 3800 at ETS, and you can see what we did in this work using a Gleeble machine, Gleeble equipment. We did compression tests at a very high temperature. As you can see here, the temperature was from 1000 centigrade until 1350 degree. So we varied between 50 degree, 30 degree, 20, and so on. This was inside the austenite phase field. This work was performed over a low carbon alloy to see if really austenite is transformed into ferrite due to dynamic transformation due to the application of stress. This was the thermomechanical schedule that we used, okay? And after having it generated those stress strain curves, as you can see. So as the temperature is increased, the peak decreased, so the level of the stress decreased as normal. Everybody knows about this. The metallurgists. And we calculated the critical stress for the onset of dynamic transformation and also the critical strain. What we used to calculate this one, so we take the stress strain curve, we apply the first derivative and we apply the second derivative. We have two minimums, and the two minimums, the first minimum is regarding to the onset of dynamic transformation, while the second minimum is related to the onset of dynamic recrystallization. And this was like shown by previous researchers where metallography techniques was taken from to prove this kind of behavior. In terms of the stress, we can see that the stress for the onset, or the initial stress to initiate the dynamic transformation is lower, a little bit lower than the onset of dynamic recrystallization. I mean dynamic recrystallization here because we have a softening behavior. It must be like also dynamic recovery, but it's like represent the softening behavior. And we have two softening behavior. We have the phase transformation, the two dynamic transformation, and also the softening that's not related to the phase transformation. When you take this stress from the curves and you trace a line over here to the x-axis, and we see the related strain or relative strain to that stress that we found, and we see that this is an interesting behavior where the critical strain it goes a little bit higher and takes a maximum point over here as the temperature increased, and also this decrease as we continue applying compression tests over the sample and increase the temperature. So this was an interesting result, and this was discussed when we calculated the volume fraction of formed ferrite, because all the samples was quenched, immediately quenched after the test. We use water to quench the sample and also to guarantee that the quench rate was high enough to prevent ferrite formation due to cooling. We took at least 10 images and used the image A to calculate the volume fraction of formed ferrite. As you can see here, this volume fraction, here is the higher volume fraction, and as we increase the temperature, there is a decrease in the volume fraction of ferrite, and over here is the minimal quantity of ferrite formed, and as the time goes up, it has a little increase in the volume fraction of ferrite. What we discussed, when you see the difference of austenite and ferrite in terms of Gibbs energy, we see that we have this behavior, and the middle way between the A3 line until the maximum temperature, we have 1008 centigrade temperature is the maximal barrier in terms of Gibbs energy difference. It means that in this temperature is the minimal quantity of ferrite that could be formed. And this also is interesting because here is the minimal amount of the ferrite that was formed, and here is the maximum critical strain to initiate for the onset of dynamic transformation. So this is a very interesting result that we found using the Gleeble 3800 machine. Also, we performed torsion experiment. We did this experiment also in the same equipment where we simulated a roughing passings, a roughing schedule. Roughing temperature, as we know, during the rolling process, we have the roughing stage, after which we have the finishing stage of the rolling process. So in this investigation, we choose to apply very high temperature. We took some schedule from the industry that we cannot show here, but we performed the simulation to see what is the behavior in terms of ferrite formation from the very rough pass. And this was performed over an X70 API X7 steel, pipeline steel. So we increase the temperature to 1200 centigrade, and also we decrease the temperature, and before the application of the first roughing pass, we waited 60 seconds for complete austenitization. After the first pass, we rapidly quenched the sample, and we calculate this rate, and this rate was approximately 500 centigrade per second. So it's impossible to form ferrite due to cooling. And also, we applied the second roughing pass. See that from the highest temperature to the lower temperature to the next temperature, we decrease the temperature about 20 centigrade. And the time between pass was 10 seconds. That's normally, it's kind of scatter is normally applied for the plate rolling simulation. After the third pass, we quench the sample. And after the fifth pass, we quench the sample as well to calculate the volume fraction of ferrite. And here we have the information about the simulation that we use. And the strain rate, it was fixed at 1 strain per second. Here we have the stress strain curve that was generated from the Gleeble machine. We applied also the double differentiation method that was proposed by John Jonas and Poliak. The second minimal, it's related to the DRX, dynamic rectalization, as you can see. And the first minimal is related to the onset of dynamic rectalization. We can see here that this have a kind of a normal and decrease a little bit this onset of strain for the dynamic rectalization or dynamic transformation. As you can see here, we have we applied the 0.3 strain to each pass. It means that for the first one, approximately 0.8 of the strain here initiated the process of phase transformation due to dynamic transformation. Or, in other words, ferrite was formed. The main flow stress, when you calculate the integrate the area over the curves, we have the main flow stress of the stress strain curve. Here for the temperatures that was used, and we see that there is a increase, but not a sharp increase. This is because we have the softening mechanism, the two softening mechanisms, the phase transformation due to DT, and also the softening mechanism due to DRX. We also perform over the quantity samples, as I said, before we had no ferrite because it was only martensite. But after the first pass, we calculated the volume fraction of ferrite was about 4% of ferrite formed at a very high temperature. And also, after the third pass, where the accumulated strain was 0.9, repetition that also have 10 seconds between times. And as the ferrite is formed, so we have 10 seconds between time. And this time between pass, the unstable ferrite or inside austenite phase field, so we have some portion amount of ferrite retransform or transform back into an austenite. In the next pass, the remaining quantity of this previous pass contribute to increase the volume fraction of ferrite in the next pass. After the third pass, this increased to about 6%. And after the last fifth pass of the roughing simulation, the volume fraction of ferrite was about 6.5 or 7%. We also performed the thermodynamic calculation where we used that approach that I showed you in the previous slides. As you can see, the Gibbs energy difference for this temperature to this material, we calculate according to the chemical composition of the material. We have the Gibbs energy difference over this range of temperature that the simulation were used. And the total vary relate to the dilatation and the shear accommodation. We have this the total vary. When we calculate, okay, the drive energy, the difference between the critical stress for the onset of BT and also the yield strength of the ferrite at that temperature, calculated and multiplied by the most oriented mid factor value, we found that all the energy that was converted to joule per mole was over the total barrier. So this explains that ferrite is also formed from the very first pass of the roughing at a very high temperature. So the industry are using the process think that only austenite to this kind of material. We need to investigate other materials or apply only rolling strain over austenite, but we have some amount of ferrite being strained that has been transformed due to the application of the stress. Okay, going on, we have also this because all of our volume fraction calculation was in direct methodology, where we quenched the sample after where we prepared the sample to do metallography technique to calculate use software the volume fraction over the ferrite and martensite, that is the previous austenite that has been transformed from the quenching process. So to have this and see, okay, what you can see, we can detect, you can do in situ detection of this kind of transformation. So the first exercise that we did, we use also Gleeble machine coupled with an X-ray diffraction beam that I'll show in the next slide about the methodology. But this was already in the previous result that we applied compression test. This means that what we did this schedule here. We increased the temperature below the A1 line until the ferrite phase. We applied the signal of X-ray, and also we did inside the double phase region, and also we did at higher temperature during the austenization process, and also applied before the application of the compression tests. And here inside the middle of the compression test we measured, and here we measure also after the application of the compression at the holding time at the temperature where the compression tests were applied. As you can see here, we have at the tested temperature here, we detected some peaks of ferrite in the plane 110, and was also existent with the austenite phase field, and also some peaks of the other austenite phase field phase peak 211 appeared during the compression test. As we finish the compression test and we hold for 5 seconds, that was this detection of the XRD 6, we still had some small amount of ferrite. So it means that after deformation at temperature above the A3 line, we had ferrite. What this means that holding time after deformation, ferrite transformed back into austenite because it's tends to go to the more stable temperature. And after 9 seconds of holding, all the ferrite vanished. This publication can be seen in this script material journal. And also it calculated this is the region where it's impossible to form ferrite according to the critical stress, as the stress peak was applied above, so it was over and overcome the total barrier. And continue with this presentation. What we did, now we did another test, not compression anymore, but we applied the tensile test. And this is the laboratory that we use in the LN Nano Brazilian Technology National Laboratory. And what we did, this is a line, the synchrotron line that provides the beams of X-ray diffraction, coupled with the experiment. The region where it was like measured according to the deformation, the sample was deformed, and also every 3 measurements per second was taken during the deformation. So the experimental setup consists of a customized Gleeble thermomechanical simulator integrated with the synchrotron X-ray beam at 12 Kiev, with the diffraction intensity measured by 2 methane silicon microstrip detector banks in a fixed incident angle geometry. We use this one, and also for the X-ray measurement. After using this, we repeat the test using a smaller Gleeble machine, a Gleeble 540 machine, to repeat the same procedure that was used this one in order to quench the samples after each quantity of applied strain. We used the same thermomechanical schedule that I show you. What we did, we quenched the sample before the application of the strain at 0.1 strain, 0.2 strain, 0.3 of strain, and also 1 minute after the strain and 3 minutes after the strain, holding time at the temperature that was kept constant after the application of the tensile test. You can see here the thermocouple was welded over the middle of the sample to guarantee that the temperature was measuring accurately. So this is the composition of the sample. You can see that it's a very low quantity of carbon, but we have a considerable amount of niobium in the other elements. The other elements not shown here because we have confidential policies in order to show the whole composition of the material. The alternate equilibrium temperature and also the parallel equilibrium temperature was calculated using the thermodynamic software, the JMath Pro. And this was the temperature of the A3 line. So the schedule here, we have here in the scale of the temperature that we use, you can see is the same as this one here. This was used in a Gleeble machine coupled with the X-ray diffraction feature. The strain, the maximum strain was 0.3, and the strain rate was 0.01, so very low strain to see the exactly confirmation of ferrite formation above. As you can see here, the A3 line temperature here is 845, well above this parallel equilibrium temperature. So you guarantee that this test was above 50 degree above the A3 line. And before 1 minute, we applied the stress over here and we hold for 6 minutes. But we quench the sample. We quench the sample for the next experiment 1 minute and 3 minutes after. This was the experiment that was done in this laboratory here, and this was the repeated one that we took in order to see the metallography, the microstructure filter in terms of the ferrite formation. Also, the CCT diagram was calculated to guarantee that the quenching time was enough to prevent the ferrite formation during cooling. The CCT diagram calculation, you see that to start forming ferrite, it's required more than 1 second, more than approximately like 2 seconds, like here, more exactly like 4 seconds to start forming ferrite during cooling. And we calculated, use the thermomechanical to calculate the velocity of quenching, and we calculated that only 0.7 seconds from 1100 centigrade to 200 degree so it's well below the A1 line, so it's impossible to form ferrite during quenching. So all the ferrite that was formed was solely due to the dynamic transformation. And here is the stress strain curve that we acquired and calculated. Use the 0.2 offset method to calculate the yield strength of the sample. And also we applied the second derivative methodology that I show you now. So the first one, we have the inflection of the curve, and when we apply the second one, we have 2 minimums. The first minimum is related to the onset of dynamic transformation, the second one for the dynamic fractionalization. When we take this value over here, we come here to the curve and we trace a line over here, and you see that this is the strain that the commence of dynamic transformation occurred. So the X-ray diffraction result. So to guarantee that everything was measured like accurately, you can see like the temperature around 450 centigrade below the A3 line that I expect only ferrite. You see the only ferrite. Between the A1 line and A3 line, when the sample was like heating to the austenite temperature, we have the double phase. Also up here, austenite and ferrite. Here, austenite and ferrite. And a little bit like over the A3 line, we can see that the quantity of ferrite decreased. And above the A3 line, we have only austenite. At the austenitization temperature, we have only austenite as well. And we decrease the temperature to the tested temperature, 1500 above the A3 line. We had only austenite phase field. So as we apply the strain, we have this interesting result. One can see that this is the time, the scale of time, because we use approximately 30 seconds to complete the 0.3 strain. And here's the laser movement, dislocation, and here's the force. As you can see here, you have like austenite, and here you start to form ferrite. As time goes by and the strains continuing, the ferrite phase field start to be more intense. And the austenite continue here, and the austenite continue here, and here we have another plane of ferrite that appeared. It means that until a certain point of strain, we had only an austenite over here and over here. As the strain increase, so starting that point, start to have ferrite formed due to strain. And here is considered as the onset of dynamic DT. As you can see here in the previous slide, you have approximately, this is the onset, and this was exactly very close to this point. So it means that the second derivative methodology, it's accurately, and also this is confirmed by the in-situ X-ray diffraction of the strain in the Gleeble machine coupled with the X-ray diffraction filter. We calculate the full wide fat half minimal to see the behavior of the plane. So we choose only 4 planes. We forgot all the planes, so we focused only on those important planes of austenite and ferrite. So as the strain continued to increase, we had at the beginning only austenite. That is increased. This means that this austenite is work hardening, and the work hardening is the onset, is the driving force for the initiation of dynamic transformation. Where this one initiate here the appearance of planes of ferrite over this strain, and also as this ferrite continues to work hardening, and after this one you see there is a decrease, a dramatically decrease in the FWHM value of this very first austenite plane. So showing that this austenite suffer dynamic rectalization. So the first minimal is related to the appearance of ferrite, and the second minimal is due to the appearance of the dynamic rectalization phenomenon that happens in the material. And the other planes of ferrite appears over here and has this unusual behavior, and also this other plane of austenite appear here and also like work hardened and also softened. And this confirms what we've been like seeing in many results so far. And also we calculate the estimation of the microstrain. So this follows the same behavior of the full width at half maximal. We use the Stokes and Wilson formula. Like to say this one, the value of this beta here is related to the plane. Okay, is this the FWHM plane. We use this one divided by 4 times the tangent of the angle where it was detected, and we see the same trend of the separate planes. It means that the right work hardened and after suffered softening behavior due to DRX, and they also the second one, while the ferrite like start to appear during the deformation and suffer work hardening, but not so intense like the austenite phase field. This is a great confirmation that dynamic transformation actually happens. This is an in-situ X-ray diffraction. So using a Gleeble machine was like a very important tool. So, and you can see that this kind of equipment can be associated with other features to have a deep investigation of physical metallurgy behavior. And using also the peaks of the austenite and ferrite, we calculate the volume fraction, where the using all the 4 planes. So we, like I said, I forgot about the other planes. So we focus on these 4 planes. So that is approximately here during the strain. We have the increase of volume fraction of ferrite, while the volume fraction of austenite decrease. Like I said before, we repeat the test in order to quench the samples. And we quench the samples, and you see that at 0.1 of strain, we have some yellow part of ferrite, 0.2 this yellow part, and 0.3 much more ferrite. When we calculated the volume fraction from the optical metallography, we see that we have this volume fraction of ferrite that is quite close, equal to this strain over here. So it's confirmed that also the methodology calculated by the indirect like a method to calculate the volume fraction from the optical microscope image, and also it's accurate process to calculate the to detect the volume fraction of ferrite due to dynamic rectalization. And then here you have like a MAV, like a this is MAV, it's SCM. Sorry, this is SCM. Okay, scanning electron microscopy technique of ferrite. You can see here we have like some quantity of ferrite. This is all martensite or bionite, like there was like previous austenite that was transformed due to quenching. Okay, and the ferrite cannot be transformed during quenching. And this, you see, much more like the future of plates of ferrite. And there's a conclusion of my work. And ferrite is formed dynamically during tensile, and it has been shown that dynamic transformation takes place 50 centigrade above the E3 by employing in-situ X-ray measurements. The driving force for the transformation is the softening associated with the phase transformation. Investigation of microstructure from the test samples has been done, and the results now will be confronted with the X-ray diffraction that we did here, and we see that the results are matched with each other. And also the presence of DT ferrite at the start of the accelerated cooling will require modification to phase transformation model. And so the industry can bear in mind that ferrite really is formed due to the application of the strain during the thermomechanical controlling process. Acknowledge the FWHM is the state from the state who founded this investigation, the institutional work here in Brazil, CNPq, the Everest company which provided sample, and also Gleeble to give me this wonderful opportunity. Thanks for watching my presentation.